So when designing your PCB stack-up, one of the most important things to have is controlled impedance. Now you want to have controlled impedance in your design for your interfaces because that helps reduce reflections. And you want to have a constant impedance all the way down through your interface line. That way you can minimize reflections and have plenty of setup and hold time and noise margin at your receiver. So when designing for controlled impedance, you need to be able to calculate that accurately. And there's two ways you can do that. You can use equations, like there's a lot of documented and established equations, supported by the IPC on how to calculate what the characteristic impedance of various structures are, say for example, a microstrip or a strip line. And you can also use a 2D field solver. And essentially what a 2D field solver is going to do, it's going to use the same geometry characteristics to trace with the dielectric height of your microstrips and strip lines, but it runs, computations on it, software computations on it, solving essentially for Maxwell's equations under certain assumptions. And it's very accurate that way to get your characteristic impedance. So what I see with a lot of people is some people don't think that impedance equations are accurate enough. Some people think that you can only use a 2D field solver. And again, each method has its pros and cons, but really for me, the important thing is to have a flow that works for you. So let me give you an example flow of something I think makes sense. So when you're first setting up your PCB stack up and you're choosing your materials and you're working with your overall thickness, you're going to start to get to the point where you want to, figure out what you want your trace width to be and your dielectrics, heights, and thicknesses to get your target impedance. Now in this case, for myself, I like to start out with equations because, for example, if you look at a microstrip equation, it can be very accurate over certain ranges. Now again, these are equations, so and they've been somewhat developed with form-fitted data. So once you get out of the range that it's acceptable in, the accuracy will be way off. So you certainly don't want to use equations as a final sign-off criteria. That's really where a 2D field solver is going to help. But for your initial placement and your initial quick ideas and planning, you can certainly use an impedance equation formula as long as it falls within the limits of the equation and figure out quickly, okay, if I've got a 5 mil microstrip trace and my dielectric height's going to be, 3 to 4 mils in thickness, that's roughly going to give me a 50-55 ohm trace. And so you can kind of use that to build your stack up from there. And then what you should do after that is once you get to a more final stack up, is you can take your stack up geometry, put it in a 2D field solver and see what you get for a value and make sure that you're within range. And like I said, lots of times for lots of structures, you're going to get pretty close to it as long as you stay within the range of the equations. And again, before you submit your PCB design for fabrication, before you sign off on it, you really should use some sort of 2D field solver to get the most accurate and final sign off with all the dielectric properties and materials and the accuracy from the vendor data sheets to get your final answer. Now some PCB fab vendors, or a lot of them these days, will actually give this data to you. They'll use a field solver for you as a final check as well. But you should do this work yourself too, because it's a good design process. It's part of the flow of making a good stack up. Now, in terms of the accuracy of the equations versus the field solver, again, they can be really good in certain ranges, but there's some things that the equations are not as accurate. For example, trying to calculate differential impedance. Instead of having like a 5% accuracy issue, you might be at 15%. And it certainly can't calculate things like crosstalk coupling coefficients, so that's where a field solver can come in handy. And then there's also some strip line offset or asymmetrical strip line structures where the impedance equations might be not as accurate as, say, for a microstrip. So you might be above a 5% accuracy issue. And again, that's where a 2D field solver comes into play. But really, going back to the equations, I find that some people are too afraid to use the equations because they don't think they're accurate enough, but I think they're kind of missing the point. That's just another tool in your toolbox, and you can use that to quickly iterate and build up your stack up as you go along. So for me, I really use them hand in hand, at the right places, because if you start out with a 2D field solver, depending on the field solver, it might be clumsy to use, or you have to have a license. And also, sometimes it'll lock you down into design decisions before you're ready to make them, right? So it's really a design trade-off. But again, I think really really they're designed to be used hand in hand from my point of view. And again, you shouldn't sign off on your design without using an accurate field solver, but you also shouldn't be afraid to use impedance equations as well. Thanks for joining me today for this coffee break video. I hope you enjoyed it. If you have any questions or feedback, or if you have a topic that you'd like me to discuss next time, send me an email at tim@signalbytestech.com, and be sure to join us online at signalbytestech.com. Sign up for our newsletter, be notified when we do another one of these videos. Now, I'm going to have another cup of coffee, and it's probably time for you to get back to work. I'll see you next time.